Hello, my name is Adam Dekich. It's May 3rd, 2026, and this is for my Chem 1020 class with Dr. Noble. It's the week 15 structure elucidation. So let's elucidate. I was in group 15, and the structure given was C6H14O, the molecular formula. And the first thing we see is the IR spectra. But actually, before we talk about that, let's talk about the degrees of unsaturation. This will tell us the ratio of hydrogens to carbons we would expect to have for a fully saturated molecule, and that will tell us if there's any double bonds or rings to be on the lookout for. So the formula is 2C plus 2 minus the hydrogens divided by 2. And now if we plug our 6 carbons in, we've got 2 times 6 is 12, plus 2 is 14, and then we subtract out the 14 hydrogens we do have, gives 0. 0 divided by 2 is 0, and that means we have 0 degrees of unsaturation. So this should be a fully saturated hydrocarbon derivative. And so let's look at the IR spectra. We've got 1, 2, 3, 4 main peaks, and I've filled out the table below here so we can just go through left to right. The first peak, this kind of fat blob, is obviously the OH group. It's classic 3200 to 3400 peak. Second peak is at around 2900 to 3000. That's the sp3ch stretch. At 1500, this number 3, we've got the sp3ch bend. And then obviously we are also on the lookout for a oxygen bond, and that would be at about 1100. We've got the carbon oxygen bend. Now, if we look at the carbon-13 NMR, this will tell us the number of unique carbon bonding environments we've got. And so you can see 1, 2, 3, 4, 5 peaks indicates 5 unique carbons. And since we've got 6 carbons total, that gives us a little hint that perhaps we've got some local symmetry to look out for. And you can see here that they're all under 100 parts per million, which would indicate they're sp3 hybridized, which is good because that's what our degrees of unsaturation told us. So if we just go down the table, we've got 22, 23, and 24 chemical shift. Upfield here are the CH3, and we've got a CH bonding environment. At 48, we've got a CH2. And at 65, we've obviously got that CO bonding environment, carbon. And this is the furthest downfield because it's the most de-shielded. So it's connected to a very electronegative atom in oxygen that steals away some of that electron density. And the more de-shielded carbon is, the further downfield it will appear in the NMR. Now, if we move on to the proton NMR, we can see the integration. So we can see how many protons and what the ratios are, which is very helpful. So we've got 1, 2, 3, 4, 5, 6 unique hydrogen environments. And that gives us a lot of information. So let's just go, actually, let's talk about the integration first. So the integration will tell us the ratio of hydrogens to each other. And so we've got 6H, 3H, 2H, 1H, 1H, and 1H. And if you add those all together, 6, 9, 11, 12, 13, 14, and we have 14 hydrogens in our structure. And so we know that this is not only the ratio, but that's the actual hydrogen count you would expect to see for these different bonding environments, which is good because that makes it a lot easier. So if we go right to left, you can see the parts per million on the x-axis here. A corresponds to this first 0.9 shift. It's got 2 peaks, and so you know that it has 1 neighboring hydrogen because of the n+1 rule, and we've got 6 of those. So I would suspect that these are 2 methyl group hydrogens, and they are probably bonded to a CH hydrogen because there's only one hydrogen on that one. And if we go further downfield, we've got B, 3H, and that's probably also a methyl group that's attached to a CH because it's a doublet, which means it has N+1, so it only has one neighboring hydrogen. The third peak here is this, what I've labeled C. It's a triplet, so this should have two neighboring hydrogens, and we have two of this type of hydrogen. And because it's a triplet, that means it's got two neighbors, and there's two hydrogens. So I would suspect that it's a CH2 with perhaps a hydrogen on either neighboring carbon. At 1.6, this D, it has 7 peaks, which would indicate it has 6 neighboring hydrogens, which I would instantly suspect perhaps be two methyl groups, which might mean that this peak and these peaks correspond to neighboring hydrogens. And we've only got one of these. And if we go even further downfield at about 4, we've got 6 peaks, which indicates that this hydrogen has 5 neighboring hydrogens. We've only got one of these. That's a sextet. And then at F, all the way down here, we've got a singlet, which means that this hydrogen does not have any neighboring hydrogens, which is very telling because we're already on the lookout for a hydroxyl group, so that's probably this hydrogen here connected to the oxygen that has no neighboring hydrogens. And so what does this tell us? This gives us all this really juicy kind of partial structure information that we can use to piece together the whole molecule. And if you piece together all these different pieces based on what their neighbors are, it's very clear that you get 4-methyl-2-pentanol. And so we've got this hydroxyl group on the number 2 carbon, and then number 3, 4 carbon has the methyl group. And so you can see this is the two CH3s that were having the same bonding environment because they're both kind of mirrored around this carbon. And so you've got 1, 2, 3, 4, 5 unique carbon bonding environments, which is what we expected. And then you've got the different ratios of hydrogens as we expected from the 1H NMR. And that's it.